Context windows have grown dramatically over the past 2 years. GPT models now support up to 200K tokens. Cloud also offers 200,000 to 1 million tokens, and Gemini Pro has been providing over 1 million tokens for a while. This capacity is sufficient to fit entire books, complete code bases, or even thousands of documents in a single prompt. Given this capability, a reasonable question emerges. If we can include everything in the context window, why should we consider building RAG infrastructure at all? The reflexive response could be that oh, RAG is still necessary, but it misses an important point. For certain use cases, long context models can generally do replace RAG. If your corpus fits within context limits, if you need cross document synthesis, if your queries require reasoning across many sources simultaneously, then including them within the full context may be actually simpler and more effective than building the RAG infrastructure. I've seen teams spend months building RAG systems when their 50 document corpus could have been handled with a simple context included approach. However, the precise question isn't whether long context can replace RAG. The question is that when it should replace RAG and when RAG remains a better approach than using longer context windows, and when can we use both approaches simultaneously. The answer depends on four factors: corpus size, cost constraints, latency requirements, and precision needs. Each factor can independently determine your architecture choice. We'll build a decision framework that will account for all four of these factors and will help you make an informed decision for your specific use case. The most sophisticated production systems today they use multiple hybrid approaches. They retrieve the relevant context to stay within reasonable token budgets, then they leverage the long context windows for synthesis and reasoning over the retrieved documents. This provides cost efficiency from retrieval combined with the reasoning depth from larger context. You are not forced to choose only one approach exclusively, so the question now becomes how you can combine both of these approaches effectively for your specific business requirements. Let's be clear when we should be skipping RAG entirely. If your corpus fits comfortably in the context, retrieval adds complexity without adding much value. A company with 50 policy documents totaling, let's say, 100,000 tokens can include everything in Claude or Gemini and can get accurate answers without building any RAG infrastructure. The entire corpus is present, nothing can be missed. Cross document reasoning happens naturally because all the documents are available simultaneously. Consider the operational difference. RAG requires you to make chunking decisions that affect retrieval quality. You need to select and potentially fine tune embedding models. You need to operate vector database infrastructure with appropriate scaling and redundancy. You need retrieval tuning to balance precision and recall. You need ongoing maintenance as documents change. Long context requires uploading documents. The complexity difference is actually substantial, and complexity has real cost in engineering time, operational burden, and potential failure modes. Synthesis tasks benefit particularly from full context availability. If users ask questions like, let's say, summarize key themes across all our quarterly reports, or let's say they ask, identify contradictions between our different policy documents, having everything in the context allows the model to reason holistically. Retrieval would force you to determine what's relevant before you know what synthesis the user requires. For a contradiction finding task, everything is potentially relevant because contradictions can exist between any pair of documents. Retrieval optimized for relevance to a query may miss documents that are relevant to each other. Small teams with limited engineering resources should evaluate long context first. The build versus buy calculus favors simplicity when you lack dedicated infrastructure teams. A startup with three engineers building their first AI feature should not be spending, let's say, 2 months on RAG infrastructure if the use case fits long context constraints. Here is the approximate threshold. If your entire corpus fits in 100,000 tokens with room for conversation history and response generation, if you don't require sub-second latency, and if the cost per query is acceptable for your expected volume, then long context may be the right choice. However, most production systems at scale exceed at least one of these constraints. So let's examine when RAG still remains pretty important. RAG dominates when your corpus exceeds context limits. A legal firm with, let's say, 500,000 documents and contracts cannot include them in any context window. A healthcare system with millions of patient records need retrieval. An e-commerce platform with product catalogs, reviews, and support tickets spanning terabytes of data has no other alternative. When your data doesn't fit, the decision is made for you. Scale demands retrieval and RAG infrastructure. Cost make RAG essential even when the context windows technically accommodate your data. Processing 200,000 tokens per query costs roughly 20 to 50 times more than processing 10,000 tokens with retrieval context. Let me make this concrete. At $10 per million input tokens, a 200,000 token query costs $2 in input alone. A 10,000 token query costs 10 cents. If you handle 100,000 queries per day, that's $200,000 daily versus $10,000 daily. The difference is $5.7 million monthly. Even with vector database costs, embedding computation, and retrieval infrastructure, RAG wins by an order of magnitude at scale. Precision requirements favor retrieval as well. So long context models suffer from the loss in the middle phenomena, where information in the middle of very long context receives less attention than information at the beginning or the end. Research from Stanford and other institutions has consistently demonstrated this attention degradation. When users need specific facts from specific documents, retrieval places that information prominently in the context. You control what the model sees and you can ensure the most relevant content appears in attention favoring positions. Freshness constraints also demand RAG infrastructure, so if your document is updated hourly, you cannot re upload everything to a context window for each query. Consider a news organization or a financial services company with real time market data. RAG systems with incremental indexing handle continuous updates gracefully. New documents become searchable within minutes or seconds. Long context approaches require explicit context management for every update, which becomes operationally prohibitive at high update frequencies. Now let's examine concrete numbers because cost often determines architecture more than any other factor. Assume GPT-4 pricing at roughly $10 per million input tokens. If you include 200,000 tokens of context per query, that's $2 per query in input costs alone. With 10,000 queries per day, you spend $20,000 daily on input tokens. That's roughly $600,000 per month before counting output tokens, API overhead, or any other infrastructure. For a venture backed startup, that's a significant runway impact. For an enterprise, that's a budget line item requires serious business justification from the finance department. RAG changes this equation completely. If retrieval returns 5,000 retrieved relevant tokens per query instead of 200,000, your input cost drops to 5 cents per query. The same 10,000 daily queries now cost $500 per day or $15,000 per month. You have essentially saved $580,000 monthly. Even accounting for vector database costs, which might run $1,000 to $5,000 monthly for managed services at this scale, plus embedding computation costs of let's say around $500 to $2,000 monthly, plus engineering time to build and maintain the system, RAG still wins decisively at this cost per price point. The economics are very important here and they really favor the RAG approach. The break-even analysis depends on query volume and corpus size. For low volume applications with small corpus, perhaps under 100 queries per day with under 50,000 tokens of content, long context simplicity may justify higher per query costs. The engineering time saved by not building RAG infrastructure might exceed the additional API cost. But this calculation changes rapidly as volume grows. Above 1,000 queries per day, you should seriously evaluate RAG economics. Above 10,000, RAG is likely mandatory for sustainable unit economics. Caching also amplifies RAG's cost advantage, so frequently asked questions hit query caches, avoiding embedding computation entirely. Popular document chunks hit retrieval caches, reducing vector database load. Production RAG systems with effective caching achieve 70 to 80% cache hit rates on FAQ heavy workloads like customer support. Long context approaches offer no equivalent caching benefit since each query processes the full context. The per query costs remain constant regardless of query popularity. This means RAG's cost advantage actually grows over time as your cache warms and common patterns emerges. Now, time to first token scales with input length. Processing 200,000 tokens before generating the first response token takes significantly longer than the processing 5,000 tokens. Users notice this delay. In conversational interfaces, latency above 1 second feels very slow. Above 2 seconds, users start to wonder if the system is broken, and above 3 seconds, pretty much users abandon the experience entirely. Their perception of intelligence correlates strongly with the responsiveness. Let me share some concrete measurements. In our testing across multiple providers, processing 200,000 tokens typically results in time to first token of 2 to 4 seconds depending on the model and the current load. Processing 10,000 tokens typically results in time to first token metric of 200 to 500 milliseconds. That's 5 to 10 times difference in perceived responsiveness. For a chatbot interface, this difference transforms the user experience from conversational to much more slower and feels like laborious, where it's like the user is still waiting for response. Retrieval adds latency, but it reduces the generation latency. A typical retrieval pipeline takes 30 to 100 milliseconds, 10 milliseconds for embedding the query with a fast embedding model, 20 to 50 milliseconds for vector search with a well-tuned HNSW index, and 10 to 30 milliseconds for cross-encoder re-ranking if you're using it. This seems like overhead until you realize it saves seconds of context processing times, and seconds matter a lot. Adding 100 milliseconds to save 2000 milliseconds is an excellent trade. The total latency improves substantially. Streaming helps perception but doesn't improve the actual latency. With long context, streaming shows tokens arriving progressively, but the time to first token still remains pretty high. Users see a loading state for 2 to 3 seconds before anything appears, then token is streams normally. With RAG based approach, the first token arrives in under a second even without streaming optimizations. The psychological difference matters here. Users who see immediate response feel that the system is working and working well. Users who wait in silence, they feel like they might abandon the experience completely and might go to a different chatbot interface. Production systems with strict latency SLAs cannot afford long context processing times. If your P99 latency target is 2 seconds, including 200,000 tokens, violates that target before generation even begins. RAG allows you to meet aggressive latency requirements while maintaining the response quality. Often, the architecture choice is dictated by latency constraints rather than the quality considerations. The needle in haystack problem is real and well documented. Research actually consistently shows that LLMs struggle to locate and use specific information buried in very long context. Information at the beginning and end of the context receives strong attention. Information in the middle receives notably weaker attention. This isn't a minor effect. Studies have shown accuracy actually drops up to 20 to 40% for information position in the middle versus the edges of long context. If a user asks about clause 47 in, let's say, a 500-page contract, including the whole contract risks the model missing specific clause entirely. The clause might appear on page 250, right in the attention dead zone. The model might confidently answer based on similar sounding clauses from page 10 or page 480 while completely missing the specific clause requested. There is a failure mode that is difficult to detect because the response sounds plausible and cites content from the document, just not the right content. Retrieval solves this by pre-selecting the relevant content. When your retrieval pipeline returns the 5 most relevant chunks, the model sees exactly what it needs to see. Nothing competes with the attention for the model. The relevant information appears prominently at the start of the context. Precision improves because the model focuses on relevant content rather than searching through everything. And you have essentially done the needle finding work before even the generation begins. However, retrieval can miss relevant context that keyword and semantic similarity don't capture. If the answer requires synthesizing information widely separated sections with no obvious lexical overlap, retrieval might miss one of the places. Consider a question like, let's say, what are the exceptions to a standard warranty term? The standard terms might be in one document, while the exceptions are scattered across amendment documents, customer specific agreements, and internal policy updates. Retrieval optimized for the query might miss some of these sources. Long context approaches never miss context because everything is present. Hybrid architectures address this trade off. Retrieve the most relevant chunks for focused context, but include the broader context when queries require synthesis. Use query classification to determine whether a query needs precise retrieval or broad context. Some queries benefit from needle finding precision, others need haystack level synthesis. Build systems that adapt to both requirements rather than optimizing for only one. The most sophisticated production systems combine both approaches rather than choosing exclusively. They use the retrieval to gather the relevant context efficiently, then leverage the long context windows for reasoning over the retrieved results. This provides context efficiency for retrieval combined with reasoning depth from larger contexts. You get the benefits of both architectures while mitigating the weakness of each. The pattern works as follows. First, retrieve the top 20 to 50 relevant chunks instead of the typical top 5. This broader retrieval ensures that you capture context that might be relevant for synthesis even if individual chunks don't score highest for a specific query. Second, include all the retrieved chunks in the context window, which might total to 20,000 to 50,000 tokens. This is more than the minimal retrieval but far less than the full corpus inclusion. Third, let the model reason across all retrieved content with full attention. You pay retrieval cost plus moderate context cost but gain synthesis capability that neither approach provides alone. Query routing determines which approach to use for each request. Factual queries, let's say, what is the refund policy, benefit from precise retrieval with minimal context. The answer exists in one location, and including extra content only risks the distraction. Synthesis queries, let's say, compare these three proposals, benefit from broader retrieval with full context inclusion because comparison requires simultaneous access to all relevant materials. Analytical queries, like let's say, summarize themes across these all documents, might warrant even broader context inclusion for a small corpus. You should build classification that routes appropriately. This can be rule based initially, checking for keywords like compare, summarize, across all, relationship between that suggests synthesis needs. As you gather data, you can train a classifier on your actual query distribution. The routing logic becomes a tunable parameter in your system, and you can adjust the balance based on observed quality and cost. This hybrid approach future-proofs the architecture. As context windows grows and costs decrease, you can gradually include more retrieved content. As retrieval improves with better embeddings or re-rankers, you can be more selective. The routing logic adapts over time based on measured performance. You're not locked into the pure RAG or pure long context approach. You can optimize the balance continuously as technology and costs evolve. Let me provide a concrete decision framework you can apply to your specific use cases. Start with the corpus size as your first filter. If your entire corpus fits in 50,000 tokens, seriously consider long context first. The simplicity advantage is real, and the operation burden of RAG may not be justified. If your corpus exceeds 500,000 tokens, RAG is mandatory regardless of other factors because no context window can accommodate your data. Between these thresholds, other factors determine the decision. Factor in the query volume as your second consideration. Below 100 queries per day, cost differences are negligible in absolute terms. A few $100 monthly difference doesn't justify engineering complexity. Choose based on simplicity and quality. Between 100 to 10,000 queries per day, run the cost calculation explicitly. The difference starts becoming more meaningful. Above the 10,000 queries per day, cost differences become substantial, potentially tens of thousands of dollars monthly. RAG's efficiency advantage compounds with volume, so calculate your expected monthly cost under both approaches before making any architectural commitments. Consider latency requirements as your third factor. If users expect sub-second responses as they do in conversation interfaces, RAG is necessary for anything beyond small corpus. You cannot achieve sub-second time to first token with 200,000 tokens of context. If users tolerate 2 to 3 second responses as they might for complex analytical queries, long context becomes viable for medium corpus. Batch processing with no latency constraints open up long context for large corpus since you can afford slower processing. Evaluate the update frequency as your fourth factor. Static corpus that rarely changes favor the simpler long context approach. You upload it once and you use it forever. Corpus with daily updates require attention to context freshness but may still work with long context if volumes are low. Corpus with hourly updates or real-time streams require RAG's incremental indexing capabilities. The operational burden of re-uploading full context after every document change becomes prohibitive at high update frequencies. You should map your situation against these four factors. Often one factor dominates and makes the decision clear. When multiple factors point in a different directions, prioritize based on your specific constraints. Cost sensitive startups might accept higher latency. Latency sensitive applications might accept higher costs. The framework helps you reason through the trade offs systematically. Let me describe specific implementation patterns for hybrid architectures. So, in this, you first retrieve the 50 candidates using fast approximate nearest neighbor search. This broad retrieval captures the content that might be relevant even if not top ranked for the specific query. Re-rank to the top 20 using cross-encoding scoring, which provides more accurate relevance assessment than embedding the similarity alone. Include all 20 chunks in context for the generation. This provides broad coverage from retrieval with synthesis capability from generous context inclusion. Hierarchical retrieval adds document level context to improve coherence. When you retrieve relevant chunks, also include their parent sections or document summaries. If three chunks come from the same document, include the document's introduction and the conclusion for framing. This helps the model understand where the chunks fit with the larger documents and prevents the fragmentation problem where isolated chunks lose meaning without surrounding context. The additional tokens are typically worth the improved coherence. Iterative retrieval handles the complex queries that cannot be satisfied in a single retrieval pass, generate an initial response, identify gaps or uncertainties in that response, retrieve the additional context to fill those gaps, and regenerate with the expanded context. This agentic pattern allows the system to retrieve context it didn't know it needed until the generation revealed the gap. Complex queries often require information that the initial required query does not obviously reference. A question about project timeline might require budget documents that only become obviously relevant after the initial analysis. Context window budgeting prevents the overflow and ensures predictable behavior. Reserve tokens for your system prompt, typically which is 500 to 1500 tokens, and reserve tokens for conversation history based on your expected conversation lengths. Reserve the tokens also for your expected response length, typically 500 to 2000 tokens, and allocate the remaining budget to retrieve context. If retrieval returns more content than budget allows, prioritize by re-ranker score and truncate the lower rank content. Never exceed the context limits. Truncation at the API level causes unexpected behavior. Budget proactively within your application. You should be building abstractions that survive architecture changes because this field evolves pretty rapidly. Your application code should request relevant context through a clean interface, not call specific retrieval functions directly. A context provider abstraction that lets you swap implementations without changing application code. Vector retrieval today, hybrid retrieval tomorrow, pure long context when the cost will drop sufficiently. So the application remains unchanged while the infrastructure evolves underneath. Consider what this looks like in practice. Your application calls something like, let's say, get relevant context, and then rather than directly invoking the Pinecone or Viviat APIs, behind that interface you can implement vector search, hybrid search, BM25, or even full context inclusion. You can A/B test different implementations. You can gradually migrate from one approach to another. The abstraction provides flexibility that direct integration does not. You should be also monitoring cost per query across both approaches continuously. So track what you actually would pay with the current retrieval versus what long context would cost for the same queries. As pricing changes and it changes frequently in this market, your data shows when switching would make sense. You should not be making guesses around economics and cost. You should be measuring actual query patterns, actual token counts, and actual costs. Data driven decisions outperform their intuition, so especially in the rapidly evolving cost landscape in Gen AI. You should be expecting that the context windows will keep growing and costs will keep falling. The trajectory is clear. What seems like a large context window today will seem like modest in 2 years. Retrieval that makes sense today might become unnecessary overhead as the context costs drop. Conversely, the corpus growth might make retrieval essential even if the context windows grows. Your document collection is not static either, so plan for adaptation in both directions. The safest approach is retrieval infrastructure with configurable context inclusion. You can always include more retrieved context in larger context windows. You can't easily add retrieval to a pure long context system because you lack the chunking, embedding, and indexing infrastructure. You should be building retrieval first, even if you include generous context. Then you should optimize how much retrieved content to include as context, economics, and capabilities evolve. This positions you to adapt regardless of how the technology develops. Now let's shift focus to conversational RAG. Most RAG resources show single turn interactions. Users send a query, system retrieves relevant documents, model generates a response, interaction is complete. This works perfectly for demos, benchmarks, and certain limited applications like document search, but it fails completely for production chatbots where users are having conversations spanning multiple turns. The gap between single turn and multi turn is substantial. Real users ask follow up questions. They ask, for example, tell me more about that, or for example, what about the pricing, or for example, can you compare the first option to the third one? These queries reference previous context. They assume shared understanding. They use pronouns without clear examples. A single turn system cannot resolve that or the first option refers to, so retrieval against your corpus fails because your documents don't contain the words like that or the first option in any meaningful way. So we need to have the shared understanding and to support the multi-turn approach. Real users change their minds mid conversation as well. They explore one direction, then they backtrack. They ask tangential questions and they return to the main topic. They expect the system to track where they are in the conversation, what's been established, what options have been discussed. Singleton systems treat every query as independent, as if the users just arrived. Users find this frustrating and unnatural. It feels like talking to someone with no short term memory. Real users build on previous answers, so if the system explains three product options, users expect to discuss those specific options in subsequent turns. They don't want to re explain which options exist, they don't want to restate the requirements as well. The users assume continuity the same way they would in conversation with a human colleague. Production systems that feel intelligent maintain this continuity seamlessly. Systems that forget every turn will feel broken even if each individual response in isolation is accurate and well informed. Building multi-turn capability requires intentional architecture. You need conversational memory to track history. You need query reformulation to transfer ambiguous queries into retrievable form. You need session management to persist state across requests, and you need context budgeting to fit history and retrieval within the token limits. None of this will happen automatically, so let's examine each component. Conversation memory maintains context across turns and is the foundation of multi-turn capability. At the minimum, you store the sequence of user messages and assistant responses. Each new query arrives with access to this history. The system can reference what was previously said, what questions were previously asked, what context was previously retrieved, and what questions were previously reached. The simplest approach includes full conversation history in every prompt, concatenate all the previous turns, add the new query, and generate. This works for short conversations, perhaps up to 10 turns, but fails as the conversations grow. A 20 turn conversation might consume 10,000 tokens of history before you add any retrieved context or system prompt. A 50 turn conversation might consume 25,000 tokens. Context budget will overflow quickly, leaving insufficient room for retrieved documents that should inform the response. Sliding window approaches keep recent turns and discard the older ones. Keep the last 5 to 10 turns. Older context drops as the new turns arrive. This prevents the overflow regardless of the conversation length but loses the important early context. If the user established preferences or constraints in turn 2 and you are now on turn 15, the sliding window might have forgotten those constraints. The system might suggest options the user already rejected or might miss the requirements the user already specified, and the users will essentially find this frustrating. Summarization preserves the important context while reducing the token count. Periodically summarize the older conversation history into a condensed form. Recent turns stay relevant for the accuracy, and older turns become the summaries that capture key points without the full detail. This balances the context preservation with token efficiency. The challenge is assuring the summaries capture what actually matters, so automated summarization can lose critical details, particularly specific numbers, names, or constraints that seem minor when stated but become important later. The right approach depends on your typical conversation patterns. Analyze how long your conversations actually run. Analyze what information early turns get referenced later, and build memory management that fits your usage patterns rather than the theoretical worst cases. Context window budgeting prevents overflow and ensures your system behaves predictably. This is an optimal complexity. Without explicit budgeting, you will encounter silent failures where context truncation causes missed information, or hard failures where API calls reject the oversized request. Neither outcome is acceptable in production. Start with your model's context limit. So, for example, 128,000 tokens for GPT-4 Turbo, or 200,000 for Cloud 3. These are hard ceilings you cannot exceed. Reserve space for expected responses length, which is typically 500 to 2000 tokens depending on your application. Long form responses need more buffer. Reserve the space for your system prompt, typically 500 to 1500 tokens. Complex system prompts with many instructions need more. The remainder is your working budget for conversation history and retrieve context. Allocate the history budget based on actual conversation patterns in your application. So, if the typical conversations run 10 turns with 200 tokens per turn, reserve the 4000 tokens for history with some buffer for longer conversations. If conversations frequently run 30 or 40 turns, you need a different strategy, likely involving summarization. Analyze your actual conversation data to set appropriate budgets. Guessing leads to either wasted capacity or whether you have included more retrieve context or overflow errors. Retrieve context fills the remaining budget after accounting for the system prompt, history, and response buffer. If you have 100k tokens remaining, you can include substantial retrieve context, perhaps 50 chunks of 2000 tokens each. If the history consumed most of your budget, retrieval must be very selective, so perhaps only 5 or 10 chunks. Dynamic budgeting adjusts the retrieval depth based on the conversation length, so short conversations get rich retrieval context, long conversations get focused retrieval to leave room for the history. You should be implementing hard limits that prevent failures. Never exceed context limits under any circumstances. If history plus retrieval would overflow, truncate the retrieval first because recent conversation context is usually more important than additional retrieved documents. If the history alone would overflow, summarize the history before proceeding. Build these chunks into your pipeline so they execute automatically. Overflowed context cause API errors or undefined truncation behavior depending on the provider. You should be budgeting your have the enforcement on your budget, so it must be strict and not advisory. Users send queries that only make sense with conversational context. For example, they say things like, "What about the second one?" Cannot this statement cannot be retrieved against your document corpus. Your vector database has no concept of the word the second one. The embedding of this query will match poorly against any document embedding because the query contains no substantive content. Retrieval fails or returns irrelevant results because the query is ambiguous without any conversation history. You need to reformulate the query into a standalone form before the retrieval. Query reformulation rewrites the ambiguous queries using conversation history. Take, for example, the statement, "What about the second one?" Plus the history, it shows the three product options which were previously discussed. Let's say product A for small teams, product B for enterprises, and product C for developers as part of the chat answer. Now it will be reformulated to something like, "Tell me about product B features and pricing for enterprise use." This standalone query can be embedded and matched against your corpus, so retrieval succeeds because the query now contains concrete searchable terms. LLM based reformulation works well in practice and is the most common approach. Prompt a fast model with recent conversation history and the new query. Ask it to rewrite the query as a standalone question that captures the user's complete intent. The model resolves the pronouns, expands the references, incorporates the relevant context from history, and produces a searchable query. This adds one LLM call per turn, perhaps 100 to 200 milliseconds with a fast model, but dramatically improves the retrieval quality. The reformulation prompt does matter. So, You should be asking for a standard question that someone, let's say, with no conversation context can understand. Ask for inclusion of relevant constraints established in the conversation. So ask for preservation of the user's specific focus and a query, let's say, what about the second one with context about comparing the product options should reformulate to include both the specific product and the comparison framing from the original discussion. Cache reformulated queries to reduce the redundant computation. If users frequently ask for similar follow ups, the reformulation patterns repeat. For example, the statement what about the option 2 after any enumerated list follows the same pattern. Store the mappings from ambiguous patterns to reformulation templates. Pattern matching can handle common cases without LLM calls. Reserve the LLM reformulation for complex cases where templates don't apply. The coreference resolution identifies what pronouns and references point to. When a user says it or that or the one you mentioned, your statement must determine what entity is being referenced. This is a classic NLP problem studied for decades with well understood approaches. Yet, production RAG systems often ignore it entirely and suffer retrieval failures as a result of it. Explicit entity tracking provides a foundation for resolution. Maintain a list of entities mentioned in the conversations, let's say products, peoples, companies, documents, concepts, and features. Track when each of them was introduced and when each of them was last referenced. When a user references it, check against the recent entities. If only one entity fits in grammatically and semantically, resolve the reference automatically. It, after discussing a single product, clearly references to that specific product. Position based references require specific handling because they are common in conversational interaction. The first one or the third option refers to the ordered items from the previous responses. If your last response listed three options, track those three options with their positions. Store not just their options were presented but their order as well. Map the statement, let's say the second one, to the second item in the list. This requires structured tracking of enumerated content, not just raw conversation history. Multiple candidate resolution handles ambiguous cases. If the user says it, but multiple entities were recently discussed, you have several options. Use recency, assuming the most recent entity. Use salience, assuming the most prominent entity. Use semantic fit, checking which entity makes sense given the query, or ask for clarification. Each approach has trade offs between smooth conversation flow and accuracy. Graceful failures matters when resolution is uncertain. If you cannot confidently resolve a reference, asking for clarification is better than guessing incorrectly. So let's say when you say the policy, the chatbot can say a statement like, let's say when you say the policy, do you mean the refund policy or the privacy policy? User will prefer a clarifying question like this or a response which about a wrong topic or the wrong answer. Confident misresolution is worse than admitted uncertainty because it wastes the user's time and more importantly, it destroys their trust. Build confidence thresholds into your resolution logic and fall back to clarification when the confidence is low. Not every turn requires fresh retrieval. If a user asks a follow up question about the same topic, previously retrieved context remains relevant. Retrieving wastes computation, adds latency, and may return identical or even inferior results if the new query is less specific than the original. Deciding when to retrieve versus reuse existing context significantly impacts both cost and quality. The topic shift detection triggers retrieval. If the user moves from asking about refund policies to asking about shipping options, the previously retrieved refund policy documents become irrelevant. You need fresh context for the new topic. Detect this shift by comparing the new query to previous queries. Embedding similarity provides a quantitative signal. If the new query embedding has low similarity to recent query embeddings, topic shift is very likely. Threshold tuning determines the sensitivity over here. Now, query complexity expansion triggers a re-retrieval even without the topic shift. If the user's follow-up requires information that's not present in the currently retrieved context, you need additional documents. So, for example, if they say, how does that compare to comparators? This statement will require comparative analysis information that's probably wasn't retrieved from the original product query. You should be detecting when follow-ups require context beyond what you have. This is harder than the topic shift detection because you're assessing coverage rather than the similarity. Staleness triggers retrieval for the time-sensitive content. If retrieved documents have timestamps and the conversation spans significant time, older retrievals may be stale. News corpus, stock information, or live imprint data becomes outdated pretty quickly. A conversation about product availability that spans 2 hours might need retrieval to confirm current stock. You should be setting staleness thresholds appropriate to your current update, content update frequency, and retrieve when the context ages beyond acceptable limits. Confidence thresholds provide another trigger here, so if your retrieval scores for the current context are low, suggesting marginal relevance, re-retrieval with the reformulated query might find better matches. You should be tracking retrieval confidence and trigger re-retrieval when the confidence drops before thresholds, even if the topic has not shifted and context isn't stale. Sometimes the original query just didn't retrieve the optimally. Session storage maintains conversation state between requests and enables stateless application architecture. In production deployments, you typically run multiple application instances behind a load balancer. Any instance might handle any request. State cannot live in instance memory because the next request might route to a different instance. Session storage solves this by persisting state externally. Stateless architectures load conversation history from storage at the start of each turn and save updates at the end. This adds latency, typically 5 to 20 milliseconds for the read and write operations combined, but enables horizontal scaling with no session affinity requirements. Any server can handle any request because all state lives in this shared storage. This architecture scales linearly with the load and this simplifies the deployment. Redis excels for the storage session storage due to speed and appropriate data structures. You should be storing the conversation history as the list keyed by the session ID. Append the new turns with rpush, which is O of 1. Retrieve the recent turns with lrange, which is O of n, in the number of turns retrieved. You should be setting the TTL for automatic session expiry after inactivity, which handles the cleanup without explicit deletion logic. Redis provides a sub-millisecond latency for these operations. The overhead is negligible compared to embedding computation, retrieval, and generation time. A session schema determines what you store and affects functionality. At minimum, store message content and role for each turn. This enables basic conversation continuity. For richer functionality, you should be storing retrieved document IDs so you can cite sources from earlier turns. You should be storing reformulated queries so you can understand how ambiguous queries were interpreted. You should be storing the extracted entities so you can resolve references efficiently. You should also be storing user preferences expressed during the conversation so you can personalize responses. Richer schemas enable smarter behavior but increase the storage requirements and serialization complexity. Session isolation prevents cross-user contamination and is critical for security. Each user's conversation exists in a separate session with a unique key. You should be never mixing session data between users under any circumstances. You should be implementing strict key isolation and audit session with the access patterns that we'll be sharing in few slides. A bug that exposes one user's conversations to another user is a serious policy violation, so you should be building isolation in your architecture from the start, but not and definitely not as an afterthought. Long conversations overflow context budgets without compression. A 50 turn conversation with 300 tokens per turn consumes 15,000 tokens of history alone. Add a 1000 token system prompt and you have used 16,000 tokens before any retrieval. If your budget for retrieve context is 10,000 tokens, you have only that remaining. A 100 turn conversation becomes impossible without compression because history alone exceeds the most context limits. Recursive summarization compresses progressively while preserving the recency detail. You should be keeping the last 5 turns vertebrum because the recent context matters most and details matters. You should be summarizing the turns 6 through 15 into a paragraph and capturing key topics and decisions. You should also consider summarizing turns 16 to 30 into a single sentence or two and capturing only the major themes. Content older than 30 turns become a brief note or is dropped entirely unless it's flagged as critical. This gradient preserves the recency while enabling the arbitrary conversation lengths. Important base compression preserves the high value turns regardless of age. So if turn 3 establishes the critical user preferences that affects all subsequent responses, keep turn 3 vertebrum regardless of the age. If turn 12 contained a decision that constrains future options, you should be preserving it. You should be also annotating the turns with importance scores based on the content type. For example, constraints, decisions, and explicit preferences should be getting high scores. Casual acknowledgements and clarifying questions should be getting low scores. You should also be compressing low importance terms first. Critical context survives even in heavily compressed histories. You should also be implementing compression triggers thoughtfully. You might compress after every 10 turns to maintain steady token usage. You might compress only when approaching budget limits to preserve the detail as long as possible. And you can also might consider this compressing more aggressively when the retrieve context requires more space. Each approach has trade-offs between the history fidelity and retrieval richness. Losing lossy compression risk, forgetting the important context, and you should acknowledge this risk. Every summarization loses the detail. Users sometimes reference specific phrasing from much earlier turns, perhaps quoting exact numbers or names that were mentioned. If the phrasing was not summarized this way, the system cannot access it and may respond inconsistently with earlier statements. Balance the compression aggressiveness against the context loss risk. You should be testing compression against real conversation patterns to ensure critical information survives. Distinguishing follow up questions from new topics affects the retrieval strategy and resource allocation. Follow ups build on the existing context and may not need fresh retrieval, say saving the computation and latency. New topics require fresh retrieval and may need history compression to make room for new context. Classification accuracy impacts both cost and quality. Lexical signals indicates the follow-up's reasonable reliability. So, for example, queries that start with and, also, and what about, and words like but and however are likely follow-ups extending or modifying the previous discussion. Queries containing pronouns with words like it, that, those, or the one reference earlier content and are definitionally follow-ups. Queries with specific entity names and not mentioned in the recent history are likely new topics introducing new subjects. Simple keyword and pattern matching catches many of these cases very computationally cheaply. Semantic similarity provides stronger signals when lexical analysis is ambiguous. For example, you should be embedding the new query and compare it to recent queries and responses. High similarity, perhaps above, let's say, zero point 0.7 cosine similarity, such as follow ups on the same topic. Low similarity, perhaps below zero point 0.4, suggests topic shift. Threshold tuning the sensitivity and requires calibration on your actual query distribution. Too aggressive towards a follow-up classification and you will miss opportunities to refresh context for new topics. And if you're being too conservative and you will use the retrieval on redundant fetches. Hybrid classification combines the signals for robust detection. You should be using lexical heuristic for clear cases where patterns strongly indicate follow-up or new topic. You should be using semantic similarity for ambiguous cases where lexical signals are absent or conflicting. You should be using LLM classification for complex cases where heuristics and similarity disagree. And also, you should also consider escalating to more expensive classification only when cheaper methods are uncertain. Most queries classify cheaply with heuristics. Reserve model based classification for the ambiguous minority. You should also be tracking classification accuracy over time. Sample classified queries and assess whether the classification was correct based on the subsequent conversation flow. If follow-ups frequently get misclassified as new topics, you are wasting retrieval. If new topics get misclassified as follow-ups, you are missing relevant context. You should be using this feedback to tune thresholds and refine heuristic continuously. Multi-turn conversations complicate the citation significantly. Singleton RAG retrieves the documents and generates a response with inline citations pointing to those documents. That is pretty straightforward. Multi-turn RAG might generate responses using context retrieve several turn goes. When a user asks for a statement, let's say, where did you get that? They expect accurate source attribution even for information surfaced early in the conversation. If you can't provide it, then it will lose the user trust. You should be maintaining citation context across turns by storing retrieval information in session state. When you retrieve documents, store the identifiers, titles, relevant snippets, and the query that triggers the retrieval. When generating responses, you should be tracking which stored documents support which claims. You should be building a mapping between response content and source documents. Even if retrieval happened 3 turns ago, you can still cite the source accurately because you stored the relationship. Citation refers the handles the document updates, so which complicates the picture further. So if a user asks about the information retrieved earlier, but the source document has not been updated, you should be deciding whether to cite the original retrieval or re-retrieve. For most applications, you should be citing what was retrieved when the information was first presented. This maintains the conversational consistency. The system said X based on document Y. If the user asks for source, you should be citing document Y even if the document Y has changed since then. Note that if users explicitly ask for updated information, which signals they want fresh retrieval, so you should be mindful of that. Explicit citation format helps user verify the claims and build trust. Include the document titles, section headers, page numbers, or paragraph identifiers when available. You should be linking to source documents when your interface supports the hyperlinks. Format citations consistently so the users know what to expect. Vague attribution, let's say statements like according to your documents or based on the information provided, will frustrate the users who want to verify specific claims. Specific citations, let's say according to 2024 Employee Handbook Section 4.3, enable the verification and demonstrate the system reliability. You should also consider the citation density. Citing every sentence becomes very visually noisy and does not improve trust beyond a certain point. You should be citing key factual claims, specific numbers, and potentially controversial statements. So, for example, you should also let the obvious inferences and connecting the language go unsighted. You should find the balance that provides accountability without cluttering the responses. Determining when a conversation continues versus start fresh affects the user experience in subtle but important ways. If a user returns after 30 minutes, should the system remember the previous context? Or after 24 hours? What about after a week? Different applications have different appropriate boundaries, and the right choice depends on users' expectations and use case. Time-based expiration provides simple, predictable boundaries. Sessions expire after a configurable inactivity period, so common thresholds are 30 minutes for customer support chat, where conversations are typically single session, 24 hours for general assistance, where users might return after later on the same day, and 7 days for personal knowledge bases, where users have ongoing research which might span multiple sessions. Sessions might also be need to be removed for Redis storage, and user returning from expiration see no history and would need to begin a new conversation. Explicit session management gives users control over conversation continuity, so you should be providing interface elements to start a new conversation or continue the previous one. You should let the users explicitly clear the history when they want a fresh start without prior context affecting the responses. Some users prefer continuity and find it valuable that the system remembers previous discussions. However, others users find accumulated history confusing or irrelevant and prefer clean starts. User control accommodates both preferences without forcing a single model. Topic-based boundaries segment the conversation internally even within a single session. A user might discuss three unrelated topics in one setting. First, asking about vacation policies, then switching to IT support, and then asking about expense reporting. Treating all these three as one continuous conversation will pollute the context. Vacation policy information is not relevant to expense reporting questions. You should be detecting major topic shifts and segments internally. Each topic segment gets its own retrieval context optimized for that topic. Segments that share only user preferences and critical established context that applies across topics. You should be also considering hybrid approaches. So, for example, you should be using topic detection to segment actively, but also respect the time boundaries. A topic begun yesterday and resumed today might warrant segment continuation if the user explicitly references the previous discussion. You should be tracking both temporal and topical signals to make nuanced boundary decisions. When RAG produces incorrect answers, you need systematic diagnosis. For example, statements like my RAG is broken is not actionable. You must determine whether the retrieval failed to find relevant documents, retrieval found documents but they were not actually relevant to the query, or the model ignored the relevant retrieved context, or the model hallucinated despite having the correct context available. Different root causes require fundamentally different fixes, so applying retrieval fixes to generation problem will waste effort. Applying generation fixes to retrieval problems will also not help. Retrieval failures mean relevant documents exist in your corpus, but they were not retrieved for your query. The query embedding did not match the document embeddings closely enough. Chunking boundaries split relevant content awkwardly, so no single chunk contained the complete answer. Metadata filters excluded relevant chunks of their documents incorrectly, so the relevant content ranked below your top K cutoff. The fix involves improving retrieval, better embeddings, different chunking strategy, adjusted filters, increased K, or hybrid retrieval combining dense and sparse approaches. Generation failures mean relevant documents were retrieved and present in the context, but the response was incorrect anyway. The model ignored the context and used parametric knowledge instead, perhaps because parametric knowledge was more consistently held. The model misinterpreted the retrieved content, extracting the wrong conclusions from the correct information. The model hallucinated details not present in the context, adding plausible but incorrect suspects. The fix involves improving the generation over here. So, for example, better prompts with stronger grounding instructions, different prompt structure, few short examples demonstrating proper context use, or different models with better grounding behavior. Distinguishing these failure modes require inspection, not guessing. So, for example, you should be looking at what was retrieved. Was it relevant? Could a human answer the question from the retrieved content? You should be looking at the response. Did it use the retrieved content? Can you trace each factual claim to specific retrieved passages? This inspection process is a debugging workflow. Without it, you're applying fixes randomly and hoping something works. This will waste time and may make things worse by obfuscating the actual problem. Let's examine specific retrieval failure modes in more detail. Embedding mismatch causes the retrieval to miss relevant documents when a user vocabulary differs from the document vocabulary. Users ask about, let's say, a statement like canceling my subscription, while documents discuss statements like service agreement termination. Semantically identical concepts, but they have lexically different expressions. Embedding models may not bridge this gap perfectly, especially for domain specific terminology or organizational jargon. Query expansion adds synonyms and related terms. Domain specific fine tuning improves the embedding alignment. Hybrid search adds the keyword matching to catch lexical variants. Chunk boundary problems split relevant content across multiple chunks. You should be considering an answer that spans two paragraphs in the source document. If your chunking created a boundary between those paragraphs, each chunk alone lacks sufficient context to answer the question. Neither chunk scores high enough for retrieval individually. The complete answer exists in your corpus, but chunks fragmented it. Overlapping chunks mitigate this by ensuring content appears in multiple chunks. Hierarchical chunking provides multiple granularities. Larger chunks capture the complete context at the cost of specificity. Metadata filter errors that exclude the relevant documents incorrectly. You filter by department, but the relevant document is miscategorized in your system. You filter by date range, but the relevant document has no date field or incorrect date. You filter by document type, but the relevant content appears in an unexpected format. You should be auditing filter logic when retrieval consistently misses documents that you know exist and are relevant. Filters are powerful for precision but dangerous if metadata quality is poor. Top K insufficiency misses relevant documents ranked just below your cutoff, so your top 5 retrieval returns documents ranked from 1 to 5. The most relevant document happens to be ranked 7 due to slight embedding differences or tie breaking randomness. Increasing top K to 10 or 20 surfaces more candidates, which you can then re rank with a cross encoder for better precision. You should be using hybrid retrieval with multiple ranking signals to improve the recall. Consider whether your precision recall trade off is appropriate collaborator for your use case. Now, let's categorize hallucination types because understanding the specific failure helps identify the fix. Intrinsic hallucination contradicts the retrieve context directly. The document says, let's say the refund window is 30 days. The model responds that the refund is available for 60 days. The correct information was present and prominent in the context. However, the model generated something totally different. This indicates a weak grounding where the model's parametric knowledge overrides the context, or attention issues where the model failed to focus on the relevant passage. Stronger grounding instructions and context ordering can help here. Extrinsic hallucination add details absent from the context, so the document describes product features, storage capacity like processor speed, display size. The model adds the pricing information not present in any retrieval document. For example, they can add, let's say, a statement like the pricing is $999. The additional information might be correct from the model's training data or might be totally incorrect. Either way, it came from parametric knowledge, not your corpus. So users may not realize which claims are grounded in your documents and which are model knowledge. This matters especially when your documents contain authoritative information that should override general knowledge. Fabricated citations claim sources that don't support the claims made. The model cites, let's say, a statement like Employee Handbook Section 3.2 for a claim about vacation policy. A user who checks Section 3.2 discovers that it discusses something else entirely or the claim is not there. The citation format looks authoritative and implies verification. Discovering the citation is wrong will damage the user trust more than an unsighted claim would, because it suggests that the system is not just uncertain but actively misleading. You should be implementing citation verification that checks whether cited passages actually supports the claims made. Confidence or uncertainty presents guesses as established facts. The model should express uncertainty when the context is ambiguous or absent. For example, a statement like "I don't see this information in the available documents," or a statement like from the model like "the document suggests X, though is not explicitly stated," would be more appropriate responses. Instead, the model states an interpretation confidently as if it was certain. Users assume confident responses are well grounded. Confident errors mislead more seriously than hedged errors because users don't know how to verify these. Calibrated uncertainty, where the confidence matches actual reliability, improves the user trust and decision making. Loss in the middle describes attention degradation in long context and is well documented in research. Information at the beginning of context receives strong attention because the model's attention mechanism emphasizes early content. Information at the end receives decent attention because recent content remains salient. Information in the middle receives notably weaker attention, sometimes dramatically so. If your most relevant retrieve chunk lands in the middle of a long context with 20 or 30 chunks, the model may effectively ignore it despite its presence. Context ordering affects the utilization and is a straightforward fix. You should be placing the most relevant retrieve chunks at the beginning of the context, not in the middle. You should be sorting by relevance score from re-ranking and place the highest scoring chunks first. Alternatively, place the most relevant chunks at both the beginning and the end, surrounding less relevant content. This simple reordering can significantly improve response quality without changing what was retrieved. You're just presenting the same information in a more attention favorable arrangement. Instruction reinforcement improves the grounding through explicit direction. Tell the model explicitly to use provided context as a primary source. Tell it to quote directly from the context when answering factual questions. Tell it to say statements like, "I don't see this information in the provided documents," when the context does not contain the answer rather than fabricating. Explicit grounding instructions counteract tendencies to use parametric knowledge. The instructions remind the model, repeatedly if necessary, that the context is authoritative for this response. Contextless limits how much the model can effectively use even within token limits. A model might effectively use 10,000 tokens but struggle with 50,000 even though 50,000 fits within the context window. Effective utilization degrades with length independent of hard token limits. Empirically test your model's effective context utilization. You should be measuring answer quality as a function of context length. You may find that retrieving less content and ensuring it's all highly relevant outperforms retrieving more content of mixed relevance. Let me describe a systematic diagnostic workflow that applies to any RAG failure. Start with the failure case. You have a specific query that produces an incorrect response. You need to understand why this specific query failed. You should not be generalizing yet. Don't assume that the problem is widespread. Focus on understanding the one case completely. Step 1. Examine what the retrieval returned. Pull the actual documents or chunks that retrieval produced for this query. Read them. Access the relevance. For example, could a knowledgeable human answer the query correctly given only these documents? If no relevant documents are retrieved, you have a retrieval problem. You should be stopping here and investigate the retrieval. No amount of generation improvement can fix absent context. The model can't use information it does not have. Step 2. You should be assessing the relevance ranking of the documents you retrieve. How relevant were the retrieved documents? Did the most relevant document rank first or did it rank fifth behind less relevant content? Did clearly relevant documents outrank relevant ones? So, for example, relevance ranking problems indicate embedding quality issues, re-ranker miscalibration, or hybrid search weighting problems. These are retrieval problems too, even though retrieval technically quote unquote worked. Improve the retrieval quality before examining the generation. Step 3. You should be examining the context utilization of relevant documents are retrieved and ranked appropriately. For example, you should be checking did the model actually use the context. Compare the response to the retrieved content word by word. Can you trace each factual claim in the response to specific passages in the retrieved context? If claims appear in the response that have no basis in the retrieved context, you have a generation problem. The model had the right information and did not use it or hallucinated beyond it. You should be strengthening grounding instructions, adjust the prompt structure, or evaluate the different models. Step 4. You should be documenting your findings. Record what you learned about this failure case. Was it retrieval or generation? What specific sub caused? This documentation builds your pattern library for faster future diagnosis. You should be building tooling to inspect retrieval because manual inspection does not scale. For any query, you should easily see what documents are retrieved, their relevant scores from both embedding similarity and re-ranking, and their actual content. A simple debug interface that shows retrieved chunks alongside the query saves hours of debugging time per incident. This is not optional infrastructure or nice to have tooling. It is essential for operating RAG systems in production. You should be comparing the retrieved chunks to expected chunks for known failure cases. When you identify a failure, determine what should have been retrieved. What documents contain the correct answer? Was it in your corpus at all? Was it chunked appropriately? Did it have correct metadata? If the expected chunk exists and indexed correctly, why did it rank lower than what was actually retrieved? This comparison identifies specific retrieval failures and points toward fixes. Relevant score distributions reveal systematic issues beyond individual failures. You should be pulling score distributions across many queries. If all retrieved chunks have low scores, typically below zero point 0.6 similarity, queries may be poorly aligned with the corpus vocabulary, or your embedding model may be poorly suited to your domain. If the scores vary widely among retrieved chunks, with first place at zero point 0.9 and fifth place at zero point 0.4, your relevance model discriminates well. If scores are uniformly high but manual inspection shows chunks are relevant, your embedding model may be poorly calibrated, assigning high similarity to semantically distant content. A/B comparisons test that retrieval changes before deployment. You should be retrieve with the current settings and propose new settings. Compare which retrieval produces better content for your set known failure cases. Critically, also compare on the queries that currently work well. Does the change improve known problems without addressing working cases? Side by side retrieval comparison prevents the fixes that solves one problem while creating others. You should never be deploying retrieval changes without regression testing. For generation problems, you should be isolating the generation step from retrieval. Take the exact context that was provided to the model for the failing query. You log this because you're following the logging practices we'll discuss later. Feed that exact context to the model again and examine what it generates. You should be checking each factual claim against the provided context. This manual inspection reveals whether the model used context appropriately. Ignore context or hallucinate beyond context. Claim extraction breaks responses into verifiable units for systematic analysis. Consider response. Then let's say the statement the refund period is 30 days requires the original receipt and includes the excludes the sales items. This contains three distinct claims: 30-day period, receipt requirement, and sale item exclusion. Check each claim against the context independently. Partial correctness is pretty common. The first two claims might be grounded in context while the third is hallucinated. Granular analysis reveals specific failure patterns that aggregate analysis misses. Attribution tracing links claims to supporting context programmatically. For each claim extracted from a response, identify which retrieved chunk, if any, supports it. If no chunk supports a claim, flag it as a potentially hallucinated. If multiple chunks conflict on a claim, flag it as ambiguously grounded. Automated attribution tracing helps scale this analysis beyond manual inspection, which is valuable when you're investigating patterns across many failures rather than the individual cases. Prompt gradient test grounding sensitivity. If the same context produces hallucinations with one prompt, but accurate responses with different prompt, your prompt weakly grounds the model. So the information was available, the model just didn't use it from the with your original prompt. You should be experimenting with the grounding instructions. Let's say statements like answer only based on the provided context, or let's say statements like quote relevant passages when answering. So you should be finding paraphrasings that reliably ground your specific model on your specific content types.